In Unit 10, we're going to continue our study of integrals, and we're going to follow two particular paths this unit. One is to extend our techniques for actually evaluating integrals in terms of finding formulas, and we're also going to look at a more qualitative question. If we have a function and we ask what its integral is, then we're building its antiderivative. But what would the graph of that look like if we maybe couldn't find a formula for that function? Let's explore that a little further. As a reminder, the fundamental theorem of calculus is stated here. The integral from a to b, which you can think of as the accumulation of f of x as an area or as a velocity, calculating distance, times little units of delta x, can be given by a simple substitution of the upper and lower limits into some new function where that new function, capital F, is any antiderivative of what we started with, little f. And so we developed this new terminology, the indefinite integral, where we said that the integral of f of x dx is the antiderivative up to some constant. And an inverse of that is the derivative of our antiderivative is the original f. So we can go from little f through an integral to capital F, and then we can go back the other way through a derivative. When we do the antiderivative or the integral step, we need the plus c because when we differentiate, we could have any value added on the end of that without any penalty. All right. So the later part of this unit will be focused on finding formulas for this step, antiderivatives based on actual formulas for f of x. But sometimes we might not be able to do that. We might have a formula for little f but not be able to find an antiderivative. So we're going to do a more qualitative study first of what the graph of capital F of x might look like given little f. We can always build the graph, at least qualitatively, even if we can't find an exact formula. Now let's consider an example. Here we have a parabolic looking shape. We don't actually have a formula, so we're not sure if that's exactly the shape it is, but it has that down then up contour. Now that's what we're going to call little f of x. And we're going to build from that our capital F of x by integrating little f of x dx. We could also go back the other way by taking a derivative. Now, of course, we have a plus c that we can consider as part of the antiderivative. We'll see that when we sketch two possible curves of this antiderivative function. So this is the reverse of what we've done before. In this case, what we have are values here, when we integrate, are going to become slopes on this graph, because when we take a function like big F of x and differentiate it, i.e. calculate the slopes, we get the y values in the derivative function. So that's going to be one of the major relationships between these two graphs. So if we take a look at our function here, this value is -3. So if we pick a starting point, we don't actually have that much information here. Let's start at 0, 0 to see what happens. We're going to have a slope of -3 because we have a value of -3 here. So slope of -3. And then as we go further, actually the slope is going to get more and more steep because the slope is going to become -4 somewhere else. So it's going to be -3. We'll do this not at a 1-to-1 scale. So -3 but getting steeper. When we reach this value here, the value here is the slope on this graph, not the other way around. So the value here is -4, it's the y-coordinate. We get a slope here of -4. And then the slope, the values here are still negative, so the slopes are still negative. The next big landmark point will be this y equals 0 point here, and that translates to somewhere on this axis here, the slope being 0. So we're going to continue on. The slopes are negative, but getting less steep until we see something likely like this. There we have a slope of 0. Afterwards, it's really more about the intervals. From 3 to 4, the y are positive, and so the slopes are positive. The y values are positive and increasing. The slopes on this interval are positive and increasing. And it's that literal a connection between the two graphs. Every y value here translates to a slope value on this graph down here. So let's sketch that out. So it's actually getting a little steeper. If you're wondering what's happening here, well, the slopes are getting steeper, that's concave down, and then the slopes are getting less steep, that's concave up. There's something about critical points and derivatives. I'll let you sort that through that logic. But this interesting point on the original graph marks a point of inflection on its antiderivative in this particular case, and that's the general theme we'll see. So that's how we can sketch one example, because we're asked to sketch two possible antiderivatives. Well, all of that information we talked about, the slopes and the slope at zero and increasing and so on, that we had no choice about, because that was defined by the function we were given to start with. What we can change is our arbitrary choice of starting points. If we choose a different starting point, we would get the same shape of graph, zero slope, increasing afterwards. We get the same shape of the graph, but it would be shifted vertically. And that, you can see graphically, is the effect of the plus c. When we differentiate either one of these curves, the vertical position doesn't matter, because all it is a translation of slopes on these graphs to this graph here when we take our derivative. But that gives us the flexibility of moving this graph up and down without having any effect on the derivative graph. We now consider an example we're more familiar with, g of x equals sine of x, and we're again going to sketch two possible antiderivatives. So the relationship again, this is our little f of x, this is our capital F. We get from here to here by doing an integral, and we get from here to here by taking a derivative. And we would have a possible plus c going on. Graphically, the y values on this graph become slopes on this graph down here. What that means for us in terms of structure is that the initial y value here is 0, so it's 0 at y. I'll do this in the same color scheme as the last example. We're going to have a slope of 0 at the initial point on this graph, and we're going to start at 0, 0 just for convenience here. Then on this interval here, we have the y values positive, and that means on this interval here, the slopes are positive. Okay, so the slopes are positive. We're going to get a graph that looks like this, and then we're going to get 0 slope. So always 0 slope to start with, then the y's get bigger, the slopes get bigger. The y's get smaller, the slopes get smaller, and then we have another y equals 0, and we have another slope equals 0 point. Then we continue on. These values of y here are negative. And so we have negative slopes. And the slopes are initially 0 and then getting negative and getting big and negative. The slopes are 0. The slopes are more and more negative until they reach a maximum negative slope, steepest negative slope, and then they bottom out. And once again, we get a y equals 0. And that means the slope equals 0. And we keep going on. So we'd have the same kind of structure. Every landmark 0 value on this graph, the y values here, represents a 0 slope on this another graph. And so we can continue on like so. That 0's there. So we get a graph something like that. And once again, that would not be the only choice. We could also move it down here if we liked and add a constant to it. So 0 slopes and up. This is meant to be a little more parallel to the other line. I hope it gives that impression. Those would be two possible antiderivative graphs based on the function here being sine of x. I just realized a little thing. I used f here. Let's change those to g's, shall we? In the interest of consistency with this page. So our g of x would go to a capital G of x. All right. So that's another sketch of an antiderivative. Now, one of the things we might want to do is get a little more precise about this. I mean, this is a rough sketch in the sense that we know the slope is 0 here and here. We know it goes up in between. The function increases from here to here. But by how much? Do we have any sense for the distance there? Well, we can find that out courtesy of the fundamental theorem of calculus. Remember that we have that area relationship, and when we're looking at functions like our little f of x that we have as an input, this is a change in the antiderivative. This is the change in the antiderivative's value. Now that's important because that's a delta y in the f of x graph. That's another way to think about it. So the area, again with quotation marks because it might be negative, but the integral value of our original function, or areas on that graph, are going to translate into the change in f, or the change in y values on the f graph when we go to sketch the antiderivative. So that's an important realization we can use with our sine graph. Because what we can do here is ask not just what's the shape of the graph. So we found the shape was 0 slope and then increasing faster and faster and then going up to here. We can actually add some more detail by measuring the area underneath this part of the curve here. All right, now how do we do that? Well, our fundamental theorem says that this is the sine graph, this arch is from 0 to pi, and so if we ask the question, what's the integral of sine x dx between 0 and pi? We know that this is our little f of x here. Actually, we call it g, we'll stick with that. Little g of x, and the antiderivative, or what I'd have to differentiate to get that value, would be cos of x with a negative sign out front. Why? Because if we differentiate cos, we get negative sine. So I want negative of negative sine. We want to evaluate that at 2 points, 0 and pi. And so we'll get negative cos of pi minus cos of 0 minus negative cos of 0. Upper value minus lower value. And it turns out that that is negative of negative 1. And cos of 0 is 1. So we get plus 1 minus another 1. And that turns out to be 2. So what that tells us here is this area is equal to 2. And so the change in g here on that same interval from here to here must be 2 as well. Areas, or integral values, equal the net change in our antiderivative function. And let's line that up a bit better just so it's crystal clear. Here's where the point would be. There we go. This gap vertically is going to be 2 because this area is 2. And so if we add that extra condition to our little table on the side here, we have integral or area values. Those translate directly into delta g or delta f values in the more general case. And we still have the relationship that y values represent slopes on the antiderivative graph. So this is our little f of x, g of x in this case, and we're building our capital G of x by integrating. We could go back and confirm things by differentiating. All right, once we do that, we start to see that the same pattern emerges, but we just had more detail added to it. So we're going to have some graph that looks like this, and up to here. There we go. The other 0 point is a 0 slope, and we know now that it's symmetric, perfectly symmetric, because the area of this arch is going to be exactly the same as this area of this arch. So this arch happens to be below the axis, so its integral would be negative. And that means this delta g here is negative 2 as we go from the starting point down to the end point at 2 pi. And with that information all together, we can get a very detailed graph of the antiderivative of sine, which turns out to be negative cos of x with a possible addition of a constant. In this particular case, this would be plus 1. The actual graph of negative cos would be a little lower. It would be symmetric across y equals 0. It would look like this. All right, so this would be another g of x alternative. So there's a fair amount of detail there, but that's the basic premise of sketching antiderivatives from a given function. The two most important features that tie this graph to the graph we're sketching, the original to the antiderivative, is that y values in the original represent slopes in the antiderivative, and that integral or area values on the original represent changes in the function on the antiderivative graph.